Hi, I'm Jim Forster. I'm with Cisco Systems. I've been with Cisco about 4 years, and in that time, I've learned some things about networking. One thing I've noticed is that in networking, current practice is closer to current research than in other fields. I like that, and I'd like to share with you some of what I've learned, and especially what I've learned about users and what they need in networks. This talk is entitled Multiprotocol Routers in Large Networks. I find it very interesting because the problems of large networks are more challenging and more diverse than those of smaller networks. To paraphrase a compiler's professor I once had, anyone can build a mediocre router for small networks, but it's very difficult to build a very good router for a large network. I'll start my talk with some basics. We'll discuss the difference between packet switching and path determination, attributes of routing protocols, how to compare metrics on different paths, classes of routing algorithms, real-world problems, advanced protocol issues, routing multiple protocols in one router, and finally I'll try and make some comments about the engineering process in a rapidly changing field such as this. Here's a very simple routing table. It lists a series of destinations, and next to each destination is the next hop to that destination. Note that it doesn't list the complete path to get to the destination. It simply tells you where to go to get to someplace closer to that destination. Here's how routing tables like this are used to traverse a network. Let's use as an example a routing problem involving 5 cities in the United States. We want to get from Los Angeles to New York. The routing table in LA says that the next hop is Dallas, so we go to Dallas. The routing table in Dallas says to get to New York, the next hop is Chicago. In Chicago, the routing table says that the next hop to New York is New York itself, so we go there. Now, if we want to go from New York to LA, we use the same algorithm and the same routing tables. But this time the routing tables take us back to LA via a different path, New York to Chicago to San Francisco to LA. There's nothing wrong with 2 directions taking a different path. We need to distinguish 2 different actions that routers perform. The first is path determination, and the second is packet forwarding. Forwarding packets is relatively easy. It consists of receiving a packet, checking the header, consulting a routing table to decide where to send it, possibly modifying the header a little bit, and then sending it out. As I said, this is fairly easy because it's not a distributed process. It's very well contained. There's a certain set of information and a very strict rules on how to do it. The challenge in switching is how to do it very quickly without requiring a lot of hardware resources. And because of this, the switching process is what tends to drive the hardware architecture in routers. Path determination, on the other hand, can be very complex. It's inherently a distributed problem. The state of the network is contained throughout the network in a number of routers. These routers must cooperate so that they all have routing tables that are consistent and so that a packet will reach the destination efficiently. A routing protocol must do several things. It must fill in the routing table, first of all, and it must be stable. That is, after a change to the network, the routing tables must change, but if the network has no more changes, then the routing table shouldn't change anymore. The routing protocol must pick a good path. Above all, it must avoid a path which has a loop. The routing protocol must be understandable. It's very important to the network managers that they understand the way the network is operating, and they can't do that if they can't understand the routing protocol. Beyond these requirements, there's a number of other attributes that a good routing protocol should have. One of these is convergence. This can be measured either in time or the number of messages that are required after a change to the network until the routers have agreed upon new paths through the network. Another attribute is the flexibility of administrative controls. It's very important to be able to control the network, and sometimes this requires fine-tuning of the network. Some routing protocols allow a wide variety of controls, and some routing protocols have limitations as to what can be controlled. Another attribute is hierarchy. Some routing protocols allow for a hierarchy, and this is a big help in scaling network to a very large size, but it does come at some expense, as we'll see later. Multipath support is another attribute. It's very nice if a routing protocol can allow multiple paths through the network to the same destination. And there are a couple ways to do that. Another attribute is adaptation to changing load. As packets flow through the network, the load in the network changes, and it's different in different parts of the network. So the best path through the network at one point in time might be different than later on as traffic increases in some portions of the network. Finally, security. Security is very important because networks are really formed as a loose confederation of administrators. And sometimes you have to have tight control over your routers and what information they will use. So security helps you achieve that. Before we can discuss how to find the best path, we have to discuss how to compare paths. To compare paths, we use metrics. And there are a number of different metrics that we can use. First metric that's commonly used is hop count, simply the number of hops through the network to the destination. A second metric that can be used is unitless numbers. Another metric is delay. Bandwidth is another. Monetary cost is a possible metric. If portions of the network will charge for the packets that are going through the network, then this is a very important metric. Other possibilities are reliability and utilization. Now, what's very important to notice is that two of these metrics, bandwidth and delay, have an enormous range. Delay can range from a few tens of microseconds up to a second, if it was over a satellite circuit or perhaps several satellite circuits. Bandwidth can range from 9.6 kbits a second up to almost a gigabit. So both of those have an enormous range, 10 to the fifth, and we'll see why that's important later on. We must consider not just the metrics of an individual link, but the metrics of the entire path. If two paths through the network have the same physical characteristic, that is, they can take the same traffic and will deliver the same number of packets in the same delay, then they should have the same metric. If one of those paths is a single hop and another path has multiple hops, then we still need those two paths to have the same metric. But the problem is we start with metrics of individual links, and we need a way to combine the metrics of a series of links into an equivalent metric that has the same behavior for the routing algorithm as a single link. We need a function that will combine the metric for two links in such a way that it yields the same metric as a single hop link with the same parameters. If you go through the list of metrics that I listed earlier, we find that addition works fine and satisfies the criteria for most of the metrics. It works for hop count, unitless numbers, delay, monetary cost, but it doesn't really work well for bandwidth. And the reason is that the bandwidth of two links in series is the minimum of those two links. It also doesn't work for reliability because the reliability of two links in series is the product of those links. So if we want to use bandwidth and reliability as part of our metric, we have to combine them appropriately using minimum and the product. Now, it's very difficult to speak of the utilization of a path, but utilization is important. So the best thing we can do with utilization is use it to modify the nominal delay using a formula from queuing theory. And this formula shows that the actual delay goes up tremendously as the utilization increases. A simple example shows the importance of properly concatenating metrics for bandwidth. In this example, there are two paths, one of which is a single hop path with a 0.5 megabit per second link. The second path has many 1.5 megabit per second links. If we were to use addition as our metric concatenation function, we choose the one hop 0.5 megabit per second link. But if we use min as our metric concatenation function, then we'll choose the mini hop path because it does have the highest bandwidth. Routing algorithms may be divided up into several classes of algorithms. The first class that is still widely used is static routing. Static routing requires that the administrator configure every entry in the routing table manually with the path that he wants to use. This has some obvious limitations. If the network changes and that path is no longer usable, then packets will still be sent that way, and that's not very good at all. But static routing does have some reasons, and it is still used today. It's a form of policy-based routing. Second major class of routing algorithms is centralized routing. In centralized routing, the entire state of the network is sent to one place. That place computes the best path and sends the routing tables to each of the nodes. This is not widely used in networking today, but has been used. Another major class of routing algorithms that is widely used is known as the distance vector algorithms. This is also known as the Bellman-Ford algorithm. The final major class of routing algorithms is the link state algorithms. These are sometimes also known as the shortest path first algorithms, after the algorithm that's used to compute the best path through it, sometimes known as the reliable broadcast algorithms, because the underlying reliable broadcast mechanism that's used. The principle in distance vector algorithms is that each router maintains its routing table, its list of destinations and costs to the destination, and it sends that routing table to all of its neighbors. Whenever a router receives such an update from its neighbors, it goes through that update entry by entry, and it takes the advertised cost, adds to that the cost associated with the link over which the update was received, and it compares that sum to the entry in the routing table. If that sum is less than the current entry, then a new, better path has been received, and the entry in the routing table is replaced. If that sum is greater than the entry in the routing table, then that update is discarded. Because yes, it was another path to the destination, but it's not as good as the current one, so we discard it. An example shows how this works. Chicago starts with no path to LA. When Dallas sends an update to Chicago, advertising LA with metric 5, adding the link cost 5, the total metric is 10, and this is put in the routing table. Chicago also receives an update from San Francisco, advertising LA at distance 7. Chicago adds the cost of the link the update is received on, 6, and compares the sum, 13, to the entry in the table. And since 13 is greater than the existing entry, the information from San Francisco is ignored. When Chicago sends an update to San Francisco, it will be ignored because the total cost will be 16. One of the problems with the simple Bellman-Ford algorithm is known as count to infinity. The count to infinity problem is as follows. In this example, B's path to C is via link X and Y. When link X fails, A updates its routing table to indicate that it can no longer reach C. Now B sends its routing table to A, which updates its routing table with a new path to C via B with metric 3. A then sends its routing table to B, which updates the metric for C from 2 to 4. B now sends its routing table to A, which must update its metric for C from 3 to 5. This process continues for several updates until the metric grows larger than the metric for link Z, 10. At this point it has converged. Up until then, the routing tables contained a loop, and any packet sent for that destination will simply bounce back and forth between those two routers. Several improvements must be made on the simple Bellman-Ford algorithm for it to be usable. These are split horizon, triggered updates, and hold down. Split horizon will solve the count to infinity problem for simple loops, for simple two-cycle loops. Its basic idea is that it is not worthwhile to send information back where it came from. It has additional benefit that it saves bandwidth, because sending information back where it came from is really worthless. Here's an example that shows how split horizon will avoid the problems in the previous example. We have the same network and the same scenario where a link fails. But in the same example as before, after link X fails, B does not send an update concerning C to A, because A was the source of the information originally. A sends its update to B, advertising unreachability. B updates its routing table to use link Z with metric 10. B then sends this to A. A updates its routing table to use the path to C via B. Split horizon does not solve all the problems with Bellman-Ford. It helped in that particular topology, but we can see another topology where it does not help, and we can still have count to infinity. In the next example, information from D may pass through A to B to C, and then back to A. Note that the split horizon rule never got a chance to be applied here. At this point, A cannot distinguish this old information from newer information received from D. And if the old information has a better metric even after passing through B and C than the new information from D, A will believe the old information. Another technique that helps a lot is triggered updates. Rather than wait for the next period to send updates concerning new information, with triggered updates, it's sent immediately to all neighbors. Triggered updates are also sometimes known as flash updates. Now, the real problem that we're fighting in Bellman-Ford with the count to infinity is that we need to avoid treating echoes of old information that are bouncing around in the network as if they were newer information. And it's somewhat difficult to distinguish the two. One direct way to combat this problem is called hold down. And in hold down, whenever a route is unreachable, we put that route in a state called hold down. And while it's in hold down, we ignore all information that we may hear about that route. We also don't say anything at all about it. During the hold down period, the echoes of this old information will die out of the network. Finally, when they're all gone, we start listening again, and whatever information we do hear then is guaranteed to be new information. Now, the time required for hold down differs and depends on the speed of the network and the size of the network. But typically, several update periods are required to ensure that the old information has died out of the network. The summary of distance vector algorithm properties is that they are simple. Even with these improvements over the simple Bellman-Ford algorithm, they're still very simple. They're computationally efficient because the major operations that we're doing are addition and comparison, and they're really a distributed calculation because each router is performing some of the calculation and it's filtering out some of the information. So when it passes new information to other routers, they're not getting the complete information about the network. They're only getting relevant information. Distance vector algorithms can be somewhat slow to converge. If hold down is used, typically 3 to 6 update periods are required. However, hold down is not always required and not always used. There are many examples of protocols which use distance vector. There's RIP, Routing Information Protocol. It's used in TCP/IP, AppleTalk, XNS, Novell IPX. About the best that can be said for RIP is that it's simple and it works okay in small networks, especially if they're homogeneous. IGRP is another distance vector algorithm. IGRP is available for TCP/IP and OSI CLNS networks. It features very nice metrics, a range of metrics are used, and it's a Cisco proprietary protocol. EGP and BGP are also distance vector protocols used for TCP/IP networks. The last protocol listed, IDRP, is a new protocol that's used for OSI CLNS networks. There are some new ideas in distance vector routing protocols, which are very interesting. First of these is known as route tagging. It's a way to avoid hold down. Each router that sends some information into the network tags that information with a timestamp-like tag. Whenever that information changes, such as a link becomes unavailable or if the link changes significantly, the router generates a new timestamp and sends that into the network. Whenever a route becomes unreachable, a particular instance of that route is put into hold down, and that timestamp is remembered. When we receive updates, we compare the timestamp tag with the entry that's in hold down. If it's different, we know that we have different information, and we can use that information immediately. If it's the same, then it indicates it's an echo of that old information that's bounced around and come back to us, so we discard it. This is a very nice way to eliminate hold down and yet still use distance vectors. Another interesting idea for distance vectors is known as path tracing. BGP and IDRP use this, and the idea in path tracing, which they use, is that the routing updates contain the complete path to the destination, not just the next hop. With this information, loop detection is very easy. When you receive an update, you examine the path that would be used to reach the destination. And if you find your own router ID in any of those path elements, then you discard the update, because to use it would imply sending a packet through a loop and back to yourself. Now there's another way to do it without sending the complete path in each update, and that is just to pass the first link from each destination. With this information, it's possible to thread together the information in the routing table and reconstruct the path. With this, we have a distributed link state algorithm in a sense, because we have very good information about all the links, but we don't have to perform all the computation in each router. Link state algorithms are the last major class of routing algorithms. In link state algorithms, the network topology is flooded to all of the routers. In order to do this, a reliable broadcast mechanism is required. Each router then computes its routing table from this topology database, typically using Dijkstra's shortest path first algorithm. SPF finds the shortest path through a graph to an arbitrary destination. Since the routers want a complete routing table, they must use the algorithm to find paths to all the destinations through the network. Here's an example of a link state or topology database for the same example network that we used earlier. After flooding of the topology, each router will have the exact same topology database. Computing the routing table from the topology database does not require much code, but it's computationally complex. Because of this, the SPF algorithm is only run when there is a change in the network. In between changes, small updates, known as keep-alives, are sent back and forth between the routers to ensure that the routers are still alive and well, and that no changes have been missed. Whenever there is a topology change in the network, that information is flooded through the network, and each router must recompute its entire routing table using the SPF algorithm. Now, in order to ensure that no information is lost during the flooding process, a reliable broadcast mechanism is needed, as mentioned. This presents a problem if there is a section of the network that is highly interconnected. Local area networks, or LANs, are very highly interconnected. All routers on a LAN are connected to each other. So the number of connections that we would need to maintain goes up n squared as the number of routers goes up to n. This would cause too much messages, too much computation. So in order to avoid this problem, link state algorithms usually have a notion of designated router. Through an election process, one of the routers is elected to become the designated router. All of the routers send their link state information to it. It in turn passes all the information that it knows back to those routers. So we no longer have n squared, but we do have to have the mechanism for the designated router election. And in case the designated router fails, we need to re-elect a new designated router. Link state algorithms feature fast convergence. Typically, after a change in the network, link state algorithms will converge in only a few seconds. This is very nice, but it comes at a bit of a price, in that the complexity to implement link state algorithms is substantially more than that of distance vectors. Sometimes as much as 5 times more code is required for a link state algorithm than for distance vector. Link states are also computationally complex. In the worst case, the SPF algorithm is order of n squared, with n is the number of nodes in the network. But for typical networks, it's really n log n. However, even this is worse than linear, and therefore there's some concern by the designers of these protocols over the scalability of this. For this reason, they engineered into the protocols a hierarchy. And so link state algorithms usually use hierarchy to overcome the scale problems. The protocol will have notion of areas and perhaps a notion of backbone to connect the areas. And these areas do solve the scale problem on one hand, but on the other hand, they also have their costs. They require engineering. Someone has to decide where the area is going to be, what are the boundaries, and they also produce non-optimal routing in some cases, although that's not too serious. Protocols which use link state algorithms are OSPF for TCP/IP and IS-to-IS for TCP/IP and ISO-CLNS. Here's an example topology for OSPF. OSPF divides its routers into two types, internal routers and area border routers. A separate link state database is flooded for each area. Each area must be connected to a backbone, which is also treated like an area. All areas must be contiguous. You must be able to reach all places in an area using only links in an area. An internal router has all its links in the same area. An area boundary router is one that has links in more than one area. Area boundary routers pass summary information to internal routers, which then can pick the best area boundary router to use if they need to go outside their area. OSPF metrics range from 1 to 64,000. A separate metric can be configured for each combination of IP type of service bits. The metric concatenation function that's used is always addition. So if you're trying to optimize for bandwidth, OSPF may not deliver the best bandwidth path. IS to IS is the other major routing protocol. It was first developed for ISO CLNS networks, but is now also used for TCP/IP networks. IS to IS also uses areas, but slightly differently than OSPF. IS to IS also has two different router types, level 1 and level 2, but it allows a router to be both level 1 and level 2. A second difference is that level 1 only routers do not have any level 2 information. Consequently, if there are several level 2 routers in an area, a level 1 only router cannot know which is the best level 2 router to use. This is the price of using hierarchy. Information hidden is information lost. If an area is partitioned, IS to IS allows that partition to be repaired if there are level 2 routers in both parts of the partition network, or the partitioned area. IS to IS metrics differ from OSPF. The metric for an individual link may only range from 1 to 63, and the metric for a path may range from 1 to 1,000. If a network has a lot of high metric paths, the limit on the metric for an entire path places a limit on the number of hops through the network. If the network has a wide range of diverse links, then it may be difficult to map the wide range of bandwidth and delay into the small range, 1 to 63, of individual link metrics. Now, the designers made the small range of metrics for a reason, and that is that if the range of metrics is small, the SPF algorithm may be optimized for this, and its complexity reduced from order of n log n to simply order of n, and this is very desirable. Also, it's worth noting that ISO CLNS networks will have more information in their routing table for the same size network than TCP/IP networks because they must route to individual hosts, not to networks. Two areas for further development in link state algorithms are incremental SPF calculation and multicast support. Incremental SPF calculation is important because we don't want to have to recalculate the entire routing table whenever any link changes. So it would be desirable to know which routes need to be recalculated. Multicast is desirable because there are some emerging applications which require multicast support, and link state is a good way to provide support for multicast in a network. Very few routing protocols use dynamic metric information, but it's very important because queuing delays can be very great. A lightly loaded link may have a delay of 10 milliseconds, but if that link has a utilization of 90%, the average delay will go up to 100 milliseconds. Here's an example that shows how the best path changes as the utilization in the network changes. In the example, if we use only static delay metrics, the best path from C to B is via D. However, if links AB, AC, and BC are at 50% utilization, while link CD is at 80%, then the best path shifts to CAB. Another valuable property is asymmetric load sharing. Many routing algorithms have the ability to load share between several paths, each of which has the same metric to the destination. But it'd be desirable to load share among several paths, even if their metric is not identical. However, to do this, each of the paths must meet a certain criteria to guarantee that there will be no looping in the network. And that is, the metric at the next hop for every path must be less than the metric for our best path. This guarantees that packets are always getting closer to the destination, and therefore they'll never come back to us. With asymmetric load sharing, what we'd like to do is send traffic proportionally to the metric. In this example, the best path is via C with metric 11. The next best path, via E with metric 14, is not usable for load sharing because E is not closer to D than our best path via C. The path via B with metric 26 is usable for load sharing because B is closer to D than our best path via C. Asymmetric load sharing is very important because lines come in a variety of speeds. We frequently want to configure more than one line in a network for redundancy reasons, but we don't necessarily want to spend the money to have two high-speed lines, so we'd like to have the backup line be a lower speed line. However, it's still expensive, and we'd like to use it while it's there. The second reason is that if we're using dynamic metric information, the metric for paths is not likely to be exactly equal. So if we want to use path sharing with dynamic metric information, we have to be able to do load sharing across unequal metric paths. So far I've talked about technical issues and solutions to those technical issues. Now I'd like to talk a little bit about some real-world issues and some solutions to those issues. The first and foremost real-world issue is that the protocols and algorithms must be understandable. This can't be overemphasized. Part of that is that we need to have configurations that are easy to understand and easy to configure. It's very nice, for instance, if the metrics to be configured correspond to real-world parameters, such as delay and bandwidth, rather than arbitrary unitless numbers. Arbitrary numbers have to be thought about and configured, and if two people think about it differently and use different numbers, then they'll have difficulty connecting their networks. But if they used real physical parameters, they won't have this problem. The problems and the solutions that I talked about in the technical section are easy compared to the problems that we find in the real world. And the solutions to some of those problems are messy. But we can't ignore them even though they have messy solutions. We have to provide solutions. A whole series of problems comes about because networks are very decentralized operationally. There is not one person running a whole large network that can dictate its operation. At best, network managers can hope to manage a portion of the network, perhaps the backbone, and they need to cooperate with people who are running other portions of the network. That cooperation sometimes works better than others. When it's not working well, they find that they have absolutely no control over portions of the network, but yet they're expected to try and use that portion of the network, and at the very least, it shouldn't damage the portion of the network they are controlling. So the network manager needs a series of tools to be able to control this strange environment he's in. The tools that he can use are to avoid certain routers altogether, just ignore them. So you configure your router so that it absolutely ignores information from another router. This is possible in some protocols and is somewhat difficult in others. Another way is that selectively fudge the metrics that are sent to you. So you do want to use routes from those other routers, but they've been configured in such a way that if you use the metrics that they sent to you as is, you'd be using them when you don't want to. Instead, you want to use them as a backup. So if you can fudge the metrics, then you can use them as a backup. In fact, a more general case of that is you might like to override metric-based path determination with administratively based path determination. Another tool is to use multiple instances of the same protocol. This allows you to fine-tune each instance for its purposes, and yet so you don't have to sacrifice one section of the network for operation of the other. Finally, another tool is administrative distance. This is a way of specifying which areas of the network are more trustworthy than other areas. All of these are a form of policy-based routing. Some of these are very crude forms, but nonetheless they are policy-based routing. There are several reasons to run multiple routing protocols. The first of which is that there are lots of different routing protocols out there. There is RIP and IGRP and sometimes hello, there's EGP, there's BGP, and all of these have to be run in the same router at certain times. Secondly, if we are trying to connect two sections of a network and they have routing protocols, the same routing protocol, but they've been configured with incompatible parameters, then a way around that problem is to run two instances of that protocol in one router and to redistribute the information between them. Theory says that this is done only at the boundaries of intra-domain routing. That is, it's done in inter-domain routing. But in practice, we find that this must be done inside a domain. And so it's very important if the routing protocol supports this. The solution to this problem is to carefully redistribute information from one routing protocol to the other. That could be from one instance of a routing protocol to another instance of that same protocol, or from one protocol to an entirely different protocol. We have to do this very carefully, however, because the metric transformation is imprecise. And if there's a path in the network where the same routes can come back to us, we might create a loop because the metric transformation will not get back to the same metric. An example of route redistribution is if a portion of the network needs to run RIP and another portion wants to run OSPF or IGRP. Where those places meet, we need to redistribute the routing information from RIP to OSPF and vice versa. Redistribution is critical for large nets because of the diversity in them. Large nets are not homogeneous. The portions of a large network are created at different times, they're administered by different people, but yet it's very powerful if we can pull them together. Redistribution allows us to do this. When we are running multiple protocols, we need a way to control their interaction. Administrative distance is a good way to do this. We assign a separate administrative distance to each routing protocol, and we choose routes that come to us from the source with the lowest administrative distance. We can use this with static routing, for instance. If we want to prefer the static route over dynamic route to the same destination, then we assign a lower administrative distance to the static routing. On the other hand, if we want to use the static routing only as a fallback in case the dynamic routing fails, then we assign a higher administrative distance to that static routing. Another real-world problem is that broadcasts sometimes need to be propagated beyond a router. Normally, broadcasts stop out a router, but there are cases when it is useful to flood broadcasts carefully beyond a router. An example is in the stock trading application. The source of the stock price wants to broadcast the information to a network. However, if the volume of information is too great to fit on one network, then we need to spread this application over multiple networks. But particular information may need to be broadcast to several networks, so we need to flood that information across a router. Now, this is really a multicast application, and multicast routing would probably be a good solution to it. But multicast support is not generally available and certainly not available in workstations. So a way to solve this real-world problem is to allow the routers to selectively broadcast the information. Finally, the biggest and most important real-world problem is that of multiple protocols. That is TCP/IP, DECnet, AppleTalk, XNS, IPX, bridging, source route bridging. These are all protocols that must be handled. In the past, these were typically handled by building wholly separate parallel networks. Organizations had a TCP/IP network, a separate IPX network, a separate bridged Ethernet network, separate bridged token ring network. It's very expensive to maintain separate networks. It takes a lot of equipment, but the cost of the lines is even greater, and the cost of administrating separate networks is even greater. Now, multi-protocol routers are a solution to this problem. If multiple boxes can solve a problem, then the same problem can be solved in one box. It will be cheaper, it will be just as fast, and it will be easier to administer. This is why multi-protocol routers are very, very important in the real world today. There are two approaches for multi-protocol routers. One approach is to treat each protocol very separately. So they are separately implemented inside the router. They must compete for the CPU resource in the router, they must compete for buffer resources, and they must share the use of the interfaces. But they can be implemented quite separately. Separate people can be assigned to them, and they really don't have to cooperate or really know about each other's existence. This is sometimes referred to as the ships in the night approach, because these separate implementations pass through the router as if they were ships in the night. Another approach to the multi-protocol problem is called integrated routing. And in this approach, a single routing protocol is used to pick paths for multiple routed protocols. IS to IS is an example of this. IS to IS has been extended so that it can provide routing information for both ISO CLNS networks and TCP/IP networks. Now, the advantages in an integrated routing approach is that there is only one routing protocol to implement, and it might also save some CPU and some network bandwidth since only one routing protocol is running. The disadvantage is that it becomes a little bit more complex. I personally think that it's easier to treat each problem individually than to smash them together and to try and solve them in an integrated fashion. And finally, I'd like to make some comments about the engineering process in a rapidly changing field such as this. There are many problems to be solved and many technologies that might be used to solve those problems. How do you decide which problems to solve and how to solve them? The best way to decide what problems to be solved is to listen to the users. Listen for the real problems they have, not just the solutions that they're proposing. Then you decide what technology to apply that will solve that problem the best. Don't over-engineer that solution. It's very easy to put in extra features that you think might be useful. Don't. Get it done sooner with only those features that are absolutely required. Engineering time is expensive because technology is moving so fast. CPUs are doubling in speed every 2 years, RAM densities are quadrupling every 3 years, and software technology is also proceeding very rapidly. When you start a project, you pretty much have to lock in the technology that's available at the start of the project. For that reason, shorter projects will have more current technology when they complete than a larger project. So this notion I call just-in-time engineering. And the idea is that you want to get your engineering effort as close to the users as possible and put in just what's required and get it to them quickly, and then get their feedback and use that to improve the next iteration of that cycle. That's an approach and a process that I find works well, and I think you'd find it work well for you too. Thank you.